So I want to do a mini side lecture here on significant figures and a brief introduction to uncertainty and a brief review of scientific notation. So to start, let's look at literally the most basic math problem we can. 1 plus 1 equals 2. But what about something like this, where you have 1 plus 1 equals 2, but we instead specify this arbitrary thing of 1.0 and 1.0 equals 2.0. So what's the difference between those two things? Well, specificity. And mathematically, there's some deep things there, but I want to, in this lecture, constrain ourselves to sort of the scientific use as regards to measurement, and we are not going to talk about the nature of the numbers themselves. This is not a course on number theory, after all. So why have this 2.0? Well, that's pretty simple in science. It's just because 2.0 represents the level of precision we have. Rather than just taking a meter stick and saying it's about a meter, you actually check and say, okay, it's a meter and I'm sure that it's 1.0 and it's not 1.1 and it's not 0.9 or anything like that. It's actually 1.0. You know, I know the answer to within 10 centimeters, definitely, so 1.0, not just 1. And then you say, okay, well, adding that to another meter, I have 2.0 meters. So then what about adding 1 plus 1.0? Well, that's just 2. And why is that? Well, it's because we're basically trying to avoid including information that we don't really have. Because we're adding 1.0, which is more specific, with just 1, which is less specific, and you go with the less specific thing. And so in the case of addition, what you look at is what we call the least significant figure. So whatever the sort of like, you look at where the decimal place is, and, however many digits there are to the right of the decimal place, you look at that between the two numbers, and whichever has the smaller number after the decimal place, that's how many you keep. But with, it's the caveat that it's not just after the decimal place. You can also do this with numbers that come before the decimal place, but we'll talk in a minute about why we use scientific notation so that we don't have to futz around with things like that. And so then I have this other example at the bottom, 1.0 plus 1.00 is equal to just 2.0, because, well, like I just said, 1.0, okay, so we have, this 0, but then this extra 0 is only on this one, right? So, on here, we don't know. And because we're adding, that's the rule. I'll talk in a minute about there's a different rule for multiplication. But let's just ask this question now. Is 2 equal to 2.0? And mathematically, that's one question, but mathematically the answer is just yes, because that's just 2 plus 0 over 10, which is just the number 2. But when we do measurements, we deal with these things called uncertainties, right? Because 2.0 is, also what you get for however many zeros you add here, right? If this is just 1.0, this will just be 2.0, no matter how precise this gets. Because again, you're adding something that's certain to something that's uncertain. And so to specify the certainty of the certain thing for your final answer is not really very sort of rigorous. And so then, well, is 1.0 equal to 1.0 plus 1.000? It depends, doesn't it? Like I said, 1 plus 1 plus 0 plus 0 plus 0 plus 0 plus 0 is certainly equal to 1 plus 1. But what about something like this, right? And at this point, then you might ask a very valid question, which is, what the heck is this thing, right? What is this plus and minus in the same symbol? And we say plus or minus. And so what the heck does that mean, right? Well, that means that I don't know if it's plus or minus. It means I'm telling you the answer is, the answer is roughly 1, but yeah, no, not quite exactly. And so, well, what do you do with that? You say, okay, I can't tell you exactly, but I can tell you that it's about 1, and it's not going to be more than 1.1, and it's not going to be less than 0.9, because I kind of did a few measurements, and, like, you know, I got some of them that were a little less, some of them were a little more, or maybe it's just, you know, you have a meter stick, and instead of having markings every centimeter, it only has markings every 10 centimeters, right? So you can't actually say, like, you know, like this 1.00, right? Would be if you actually measured all the way down to the centimeter marks on a meter, versus this would be if you only measured, like, every 10 centimeters. Or equivalently, if you added another, right, you know, if you looked at another one that with a, you know, 1.000, that would be if you looked all the way to the millimeters. And so you see, this upper line is equal because this is just you know, arithmetic expression, but this thing on the bottom kind of isn't, right? Because you know, adding this uncertain thing to a number, and adding this other uncertain thing to a number, which, you know, these I wrote these as just 1, but that's just 1 with one significant figure. It's still an uncertain quantity. And so we have to combine things in this sort of intelligent manner. And so if you when you're dealing with measurements, even if you don't see that little plus or minus symbol, we deal with that plus or minus symbol implicitly by use of something called significant figures, which significant figures are sort of a poor man's statistics. And the reason for that is just if you're not really looking to write down what the actual uncertainty is, but you just want to keep vaguely track of how much precision you have, significant figures are a really intelligent way to do that. And the other thing, of course, is if you actually do start adding real uncertainties into the mix, you need to write them down in a reasonable manner. And so it doesn't make sense to write down digits that are past your own uncertainty, right? So it's just an intelligent way to deal with that. And so, you know, let's look at this basic problem again of 1 plus 1 equals to 2. Or, you know, does it? Is it really so simple? And the answer is, of course, well, sort of. It's you know, let's do an aside though, and remember how this thing called scientific notation works, right? Where we say, you know, we write numbers multiplied by a power of 10, and then what we do is we never ever write a number bigger than 9.999, right? Once we get to 10, instead of writing 10 times 10 to the something, which would be stupid, we just, you know, go back to 1 and then increase this power of 10. Or likewise, if you're dealing with very, very small fractions instead of very, very large numbers, you just do it with a negative power of 10, right? Because remember, negative exponents is just fraction. And so you can do it with 1 part in 100 or 1 part in 1,000 instead of 1,000 or 100. So, but here I've just written out that same simple problem, right, of 1.1 times 10 to the 0 plus 1 times 10 to the 0 is equal to 2 times 10 to the 0, which is just the number 2, right? That is all plain and simple. But what about this more complicated thing that I've you know, written down below of, well, okay, that's also just the number, you know, 1 times 10 to the 2 plus 1 times 10 to the 0, that's just 100 plus 1, which is equal to 1.0 times 10 to the second power, which is equal to 101. So that's the scientific notation to represent the number 2 and the number 101, and the addition problem 1 plus 1, and the addition problem 1 plus 100. And so then down below, starting to have something that is also numbers, but that looks a little bit more like a measurement, but these could still technically be just numbers, right? And so that's part of the reason to use scientific notation is, in my notes at least, if you see something in scientific notation like this, it typically is a measurement or at least a numerically computed value and not an actual number, right? It's not a measurement, it's a number if you see it written as a number, but if you see it written in scientific notation, it is a measurement. Let's not get too confused. And so what about numbers like the square root of 2 and pi? Well, those are irrational numbers, and so this is a bit of a lead-in to the normal lectures, but let's not go down that rabbit hole too much just yet, other than to just remind ourselves how scientific notation sort of works, because here, let's look at this. 5.0 times 10 to the 0 plus 6.0 times 10 to the 0. That's just 11.0 times 10 to the 0, which is just equal to the number 11. You see, there, the significant figures are being dropped at the very end, and we're saying it's just the number 11, because you can also just represent numbers this way, right? And then 5.1 times 10 to the 0 plus 6.0 times 10 to the 0 is equal to 11.1 times 10 to the 0, which is equal to 11 plus 1/10. So you can use it for numbers, but typically we're going to do it if we're talking about measurements. And so what's the difference? Well, the difference is numbers are these abstract mathematical things. Measurements are actual quantities that come with uncertainties. And so we want to represent them in this format so that we can, one, avoid having to write out extremely huge and extremely small powers of, extremely huge and extremely small numbers, which I'll show on the next slide why we do that. But also to deal with uncertainties in an intelligent manner by keeping our significant figures nice and clean, because that way we never have a number greater than 10. Again, sorry, we never write down a number greater than 10, and then we write down times 10 to the as our way to imply that if you actually did write it out, it would look like this. This insane thing, right? That's, takes up the entire page. So that's a number called Avogadro's number, which technically is an integer. But it's an integer that we're not quite sure what it is. Versus pi is a irrational number, but it's an actual mathematical constant, right? Pi is not something that, arguably it is something that we have to determine it empirically because it's an irrational number, but it's universal. And we don't have to conduct any scientific experiments to measure it. We just have to do mathematical approximations rather than being able to write down an exact fraction. And so the approximation we typically use is a decimal number, where we're really writing out fractions of 10. And so I've just written what happens if you multiply pi by these different powers of 10, and you just, of course, start getting larger and larger numbers, and you never start getting zeros coming in, right? Versus if this were a measurement, what would eventually happen is you multiply by a large enough power of 10, you just start getting 0, 0, 0, 0, 0, because, it's at that point we don't have the information. And so it really shouldn't be an endless string of zeros. It should really just truncate at that point. And so that's why we use scientific notation for measurements, and typically not for sort of mathematics in the abstract. But let's continue with this example of Avogadro's number for just a minute. And because that's a real big number, and so you see why 6.02 times 10 to the 23rd, you could see where we'd want to write that in that form instead of the way I did below with, it's not quite 23 zeros, but it is 23 digits that I had to write down. But it's not an exact number, right? It's a measurement that we're uncertain about. And so even though in principle it's an integer you could count to, we just don't know exactly what it is. And so we still want to represent it in this format. And so here I've written it out with the actual uncertainties that I looked up on Wikipedia. And so, because you see, I say an exact, because in principle it's an exact integer, but we don't really know what it is. So practically speaking, it's this measured quantity. And if you don't, Avogadro's number happens to be the number of atoms in a mole in chemistry. So it's technically an integer, but it's, how many individual atoms does it take up to make a, quantity of substance that makes typically a few grams. So it's a very large number, and we couldn't possibly measure it down precisely to the level of like a single integer digit. That would be 1 part in 10 to the 23rd, which is better than the precision that we have on anything. Even quantum electrodynamics isn't that good. And so what about something like simple, like 1.0 liters plus 2.0 liters? That's just 3.0 liters. Just pretend the liters are atoms, and remember that nukes are a thing. So, our units are kind of a little bit loosey-goosey, but, we'll talk about that in greater detail in the actual course. So here is my final slide actually showing the notation. So I think that it's better to just start doing stuff and then explain the notation as you go than it is to declare your notation and say how important the notation is and proceed from there. So here it is finally written out. So there's the significant figures, which there are 3 of them because, like I said, there's these 1, 2, 3, 5, 6, 7. I just, easy numbers to pick, so I was choosing them arbitrarily. And multiplied by 10 to the 42 because Douglas Adams. And that's what we call the order of magnitude. So order of magnitude technically refers to the power that you raise any number to. But typically when we say that, we mean a power of 10. So if you're confused what people mean when they say order of magnitude, it just means a factor of 10 or multiplying by 10 or potentially dividing by 10. And then over here is the uncertainty, which is exactly that. It's the uncertainty in the measurement. And you'll notice 2 times 10 to the 40th power is 2 orders of magnitude, 2 powers of 10, smaller than this number over here. And so what would plus or minus 2 times 10 to the 40 be? So 2 orders of magnitude smaller, right? So we just go, from this 5 over 2 places, 1, 2 to the 7. So it'd be plus or minus 2 in that decimal place. So it'd be like, so it's somewhere between 5.65 and 5.69-ish. But we don't know exactly. And so we have uncertainty, which is the plus or minus thing. We have significant figures, which in this case is 3, and it's how many digits do you write down before this multiplication by some power of 10, and then the power of 10 that we multiply by is referred to as the order of magnitude. So that's my brief lecture on uncertainty, significant figures, and a review of scientific notation. Thank you for watching.